Hello, everybody. Welcome back. I know that today is a little bit packed full of things that we're going to be doing. There's not only the chi-square lecture, which I have right here for you, but also an in-class assignment on chi-square, which kicks off the next SPSS assignment, number 5. And also represents the last day for you to turn in SPSS assignment number 4. That's due by midnight tonight. So it's kind of a big day, and it's one day after your lecture. But with just a little bit of compactness at the end here, we're actually going to be able to cover everything that we typically would have covered with a little bit of breathing room over the course of the regular semester. So without too much pain, let's get at it and give you another tool in your toolbox, which is called the chi-square test of independence. Here's why we need it. At this point, you might be thinking, you know what? I've got a lot of statistical tests already. Maybe we can call it a day. I think I got what I need. And the answer to that is no. We've spent a lot of time kind of establishing what it means to do a statistical test, what it means to do a hypothesis test, a lot of the basic concepts that we had to cover. And now we're kind of rapid fire going through the different tests that you can do. Why do we need so many? And here's why. The test that you're going to use is not really so much a matter of personal preference. It's not really a matter so much of the question that you're trying to answer. The test that you use is driven by the kind of data that you gathered in the first place, which has to do with how you set up your study. Setting up a study is what you're going to learn in Psychology 301, which is why you have to have these statistics ready to go to meet the demands of however it is that you set up your experiment or your study. So far, what we've done is compare one variable to another variable. That's all that we've been doing in this class. What we're trying to figure out every time is whether the two variables have a statistically significant relationship to each other. I'm going to start with the t-test. The t-test occurred when you had one variable that served to make categories out of people and another variable that served to measure something on an interval or ratio scale for each one of those people. All right? Now, the t-test was used specifically when that category made 2 and only 2 groups out of the people, right? So categorical variable here, something that you're measuring in terms of a continuous or ratio variable here, and then you compare the mean of one group to the mean of the other group to see if there is a significant relationship between group membership and the thing that you were measuring. Okay, so this could be as easy as GPA and class standing. So if freshmen and sophomores fall in one group, juniors and seniors fall in another group, that is your categorical variable, and then you measure GPA for every single one of those people. You get an average GPA for underclassmen, an average GPA for upperclassmen, and you use a t-test to compare them. All right, what if we wanted to do all 4 classes, freshman, sophomore, junior, senior, each being their own separate category, and to see if your year in school is related to your GPA in any way at all? That would be an ANOVA. We still have one variable that makes groups out of people. In this case, it's 4 groups. And within those groups, we're still measuring continuous or ratio variable, GPA. So if you have more than 2 groups, you need the analysis of variance. Little secret, a t-test is really mathematically and conceptually nothing more than an ANOVA with 2 groups. But that's besides the point. So you would need an ANOVA if you've got one variable that makes a lot of groups and another variable that has a continuous or ratio variable. Now, what happens when you fall out of that pattern of having one categorical and one continuous variable? That's what we're doing today. If what you measure from each person is a category on one variable and then another category on another variable, you want to have a statistical process by which you can compare category membership over here to category membership over here and see if those 2 categorical memberships are related. So something along these lines. Freshman, sophomore, junior, senior is one category, but Greek and non-Greek is another category. If you wanted to know whether seniors or juniors or freshmen or sophomores were more or less likely to be Greek based on their class membership, then you would need to run a chi-square, because every single person would give you their measurement on two variables: their class, one that's a categorical variable, and whether they're Greek or not. Also another variable. So putting those two variables together, both of them categorical variables, would require something that we haven't done before, and that's the chi-square. Now, just to preview, what if you didn't have any categorical variables? What if you didn't have any way to make groups out of people at all? Everybody was just in the same group, but they're giving two continuous variables, one for each person, and you want to see if those two variables had any relationship to each other. Well, that's chapter 12. You need a correlation coefficient for that. So if everybody was giving you both a GPA and an SAT score, for instance, over the entire student body, well, you don't have groups that you're making out of people. You don't have freshman, sophomore. You don't have Greek, non-Greek. You don't have upperclassmen, lowerclassmen. You just have one continuous variable GPA, one continuous variable SAT, and you're trying to see whether those two are related to each other. That's going to be a correlation coefficient. So between all of these statistical tests, we really have our bases covered for the most part, as long as we're dealing with only two variables. After that, you have to end up doing the stuff that Dr. Marshall teaches in his 400 level class, doing multivariate analysis, but we're not even going to go there. All right. Chi-square is going to be our one and only example of what's known, by the way, as a non-parametric test. There are a lot of non-parametric tests. Most of them are kind of minor. Not very many of them are famous. Chi-square is the most famous and most often used. But the thing about a chi-square is that it is actually a measurement of exact probability for a finite number of outcomes. It doesn't rely on getting a normal or a t-distribution for a parameter around some sort of curve. It really deals with a very large and complex number of discrete possibilities and then adds them up to give an overall possibility. So that's not really going to affect a lot about how we do the procedure. You're still going to just memorize the procedure, but you should know that chi-square is an example of what we call a non-parametric statistical test. Its proper full name is the chi-square test of independence. What we are measuring for, what we are looking for, what we're trying to establish is whether how a person is categorized on one variable has a relationship or doesn't have a relationship to how they are categorized on another variable. If they are independent, then what we will get is a null result for the chi-square. If categorization over here is independent of your categorization over here, there's no relationship, no effect, and the null hypothesis is true. The other possibility is that they are dependent. That will create a different number for the chi-square test, and it will cause us to establish that there was a relationship between categorization on one variable and categorization on another variable. All right, let's get out of the abstract. Let's get into the specific. I'm going to run this first example by taking two categorical variables from a hypothetical group of people. All right, the first one is your origin on the planet. You can either be Canadian, from the US, or from anywhere else in the world. How is that for Euro-North Americentric? Okay, it's either Canada, US, or everybody else. But that's one category. Okay, there's only three possibilities, and there's another category, a whole nother variable that may or may not have anything to do with your place in the world, your geographical location in the world. And that is, if you had to choose your favorite sport of the three sports that I give you, would it be hockey, football, or soccer? Okay. If you're elsewhere in the world, you might call football soccer, but you know what? Forget it. We're in America right now. We're going to call football football. We're going to call soccer soccer. Okay. So that's what we got here. We have one variable, which is where are you in the world, with three possibilities. Another variable, which is what is your favorite sport, and that has three possibilities as well. What we're looking to determine is whether your favorite sport has anything to do with where you are in the world, or conversely, whether where you are in the world has anything to do with your favorite sport. It doesn't matter which direction, doesn't matter what the cause is at all. We're just looking for a relationship, right? So chi-square is fundamentally asking the same thing as every hypothesis test that we've done so far. Does one thing have a mathematical statistical relationship with another thing? But again, we're doing this with a different procedure because we've got a different kind of variable. All right. Here's just a quick hypothetical example in case it helps anybody clear up the difference between when we would use a chi-square and when we would use, say, an ANOVA. Here's what this study might look like if it was appropriate for an ANOVA. We would change what we were asking. We would change the nature of the variables. Okay, we would change the setup. So let's say I wanted to measure whether your origin in the world affected not how you categorize according to favorite sport, but affected how much you liked football. That would mean that our favorite sport categorical variable that we were working with has now been changed into an interval ratio continuous variable if I had everybody answer from a scale from 1 to 100, how much do you like football? In that case, I'd get an average for all the people from the US, I'd get an average for people from Canada, and I'd get an average for people from the world. Those would be 3x bars for 3 different categories. I'd put them into an ANOVA, but we're not doing that. We're not measuring anybody. We're not measuring anything from anybody that would allow us to make a mean. What we're doing is just making people sort themselves into categories, right? So chi-square is about categories. It's about nominal variables. The null of the chi-square is this statement. I'm not going to state it mathematically, but what I'm going to say is that a chi-square null states that any what looks like might be perceived association between the two categories or variables is something that was simply due to a certain amount of error or chance in sampling. Okay, that's certainly a possibility. We're still going to be taking samples, and samples are still just reflections or shadows of their overall populations. And so we're going to be taking the possibility of sampling error into account. And so when we finally decide whether a chi-square is significant or not, we're going to be asking if we think we've observed an association, is that association strong enough that it is unlikely simply to have been done by the weirdness and randomness of who made it into our sample. The alternative hypothesis for chi-square is that, you know what, there really is an association between how you categorize on one variable and how you categorize on another variable, and it wasn't just due to sampling error, it wasn't just due to chance. If you have a significant chi-square, you're in a situation where if you know something about somebody in terms of their category membership over here, you've got better information than you did before about how likely they are to categorize over here. You won't know for sure. It's not going to have to be perfect. But if you gain extra information from knowing where somebody is in the world when it comes to guessing what their favorite sport is, that's a reflection of a situation where you had a significant non-independent, that is to say, dependent relationship between those two categories. All right? Those are the concepts. That's the setup. That's how we would interpret this stuff by the end of it. So what I want to do is give you a couple of mock hypothetical data sets to demonstrate what I mean by a no contingency, no relationship, no result looking set of data, and one that clearly does have a relationship so you can get an idea about where we might be heading. In this example, I asked 92 people from the US, 92 people from Canada, and 92 people from the rest of the world about what their favorite sport was. It turns out that I got 60 people who like hockey, 60 people who like soccer, and 156 people who like football. This setup right here, by the way, is called a contingency table. It's how we're going to organize all of the information that we process again and again for a chi-square. It's a very convenient way to set things up, okay? That is, anybody who is from the US is going to fall somewhere in this column. Anybody who likes hockey is going to fall somewhere in this row. So this data, the way it's set up, is basically if I had randomly chosen, plucked out of the world population, 276 people, and I had set up on a grid on a football field, and I said, hey, this box right here is for everybody from the US who likes hockey. If you're from the US and you like hockey, go stand in that box. This box is for everybody from Canada who likes football. If you're from Canada and you like football, go stand in that box. And these numbers represent the number of people who ended up standing in that category. It's not a measure of, again, how Canadian they are or how big a soccer fan they are or anything else like that. One person standing in that block is a frequency. They are a frequency of one. They happened once. So the number of times that somebody from around the world enjoyed hockey, in this sample, it happened 20 times. So this is a contingency table for frequencies. How often did a thing happen? This is a no relationship contingency table, and I'll tell you why. If I know that you are a hockey fan, I do not have any better information than I did before about whether you're likely to be from the USA, from Canada, or for the rest of the world, because there are 20 people from each. Okay, same thing for soccer, same thing for football. Just because I know you're a football fan, well, equal numbers of people like uh, football from the USA, from Canada, and from the world. If I know that you're from Canada, that doesn't give me any more information than I had before about how likely you are to like football. Here's the tricky point. If I know you're from Canada, I know that you are probably, relative to being a hockey fan or relative to being a soccer fan, going to like football, because 52 Canadians like football, but only 40 Canadians like the other sports. So there's a good bet that you're going to be a football fan. But that doesn't change based on whether I know you're from Canada or from the rest of the world or from the USA, because the story for each one of those origins is exactly the same. If I didn't know where you were from, I would say that there's a 52 out of 92 chance that you like football. If I say, oh, and that person's from America, my guess doesn't change a bit. I stay exactly where I was. My odds of being right about how much you like, about whether you like football, is exactly the same as it was before I knew your origin. That's why this is a no relationship setup. Information about one category doesn't give you any more information about what's likely to happen in the other category. Here, however, is a setup where the hypothetical data set gives a clear indication that there's a relationship between origin and favorite sport. All right. So let's say that I knew you were a hockey fan. Well, there are 60 hockey fans, but 40 of them are Canadian. All right. So if I knew that you were a hockey fan, I'm going to put my money on the idea that you are probably Canadian. If you're a soccer fan, there are 60 soccer fans, but 40 of them are from elsewhere in the world. So if all I know is that you're a soccer fan, I'm going to up my guess, my probability that you are from someplace other than the US or Canada, all right, relative to previous information. If you're a football fan, I'm going to guess that you are from the US. Even more importantly, if I know you're Canadian, I'm going to guess that you are a hockey fan. Same thing over here for the world of soccer. Same thing over here for the world of USA and football. Okay, so you get where that comes out. If I didn't know where you were from at all, and all I knew is that there were equal numbers of hockey, soccer, and football fans in this sample, then I would say, it's a toss-up. I don't have any particular guess. I'm just going to flip a three-sided coin and guess what your favorite sport is, soccer. But now if I add world origin information to that guess, and I say, you're from the US, my guess has now changed. I'm going to put my money on football. Okay? So that's what it looks like to have a clear relationship between the two variables. Now let's express the strength of that relationship mathematically in a way that accounts for all the different weirdness that can happen in a chi-square. All right. So I'm going to stick with the same setup, but I'm going to give us a different raw data set and start tracking the different steps of what you need to do in order to do a chi-square. Anytime for the rest of this lecture that I have a number in red, that is known as an observed frequency. That is your raw data. That is the number of actual people who met the criteria to be in that box, right? So what this means is that I asked 98 people for my study, and 11 of those people were from elsewhere in the world and they liked football. 17 of those people were Canadians who liked hockey. All right, so those are the red. That is your raw data. That's what you've actually written down, ticked down in your book when you're collecting data. These blue numbers over here on the edges are known as the marginal frequencies or marginal totals. They are in the margins. They are on the far right or they are on the bottom. All that is the total of everybody who is in the row here to make 32 or the column here to make 33. That is to say, if 32 is the number in the marginal total to the right of the row that's labeled hockey, that means there were 32 hockey fans in the sample, regardless of origin. And there were also 32 Canadians in the sample, regardless of their favorite sport. Okay, so the reason we're going to need the marginal totals is going to come clear in a second, but I want to set them apart as a different color because the marginal totals are the result of adding up the original observed frequencies, but they will soon become more important than the observed frequencies. All right, that's because the third color code for numbers that we're going to talk about, it's going to be purple, is what is known as the expected frequencies. All right, the expected frequencies are this. For every category combination that we have in our chi-square, people from the US who like soccer, people from the US who like hockey, people from the US who like football, Canada, all nine categories that we're dealing with in this chi-square have a number associated with them that would be true if there was exactly zero relationship between your favorite sport and your place of origin. For that category, that's known as the expected frequency. It is given that we have a certain number of people from each origin, from the raw data, and that we have a certain number of people who like each sport overall, again, something we got from the raw data, what would we expect the observed frequencies in each box to be if there was absolutely no association whatsoever between where you're from and what sport you like? This, by the way, is going to be the first time when we start dealing with numbers that are not whole numbers. Up to this point, there's been no possibility of any fractions, any partial person. But now, these expected frequencies being mathematical constructs are going to involve the possibility of like a half a person or a decimal proportion of a person. All right. In order to do this, I'm going to quickly step out of the example that we were using, step into a new one for just one slide, because we've already been kind of poisoned by the idea that we know what the observed frequencies are in the Canada sport thing. All right. What I want to do now is ask people, is set up a new situation where I've asked 200 people two things. What's your favorite color? And what's your favorite fruit? All right. I'm not dealing at all with the observed frequencies. All right. I didn't even give you the raw data. The only thing that we know is that of these 200 people that were asked, 40 of them said that their favorite color was purple, and 20 of them said that their favorite fruit was an apple. Okay? With only this information, I can figure out how many people I would expect to be apple purple people if there's no relationship between your favorite fruit and your favorite color. Okay? So the proportion of people who prefer purple, why did I make this so hard on my articulators? All right. Anyway, the proportion of people who prefer purple is actually 40 out of 200. Got it? 40 divided by 200, that's 0.2. The proportion of people who prefer apples is 20 out of those 200, that's 0.1. So if you have 1 out of every 10 people like apples and 2 out of every 10 people who like purple, then 1 out of 10 of 2 out of 10 is how many people you would expect to overlap in that category. That is to say, you would take 40 over 200, multiply it by 20 over 200 in order to get the answer in here. All right, so 40 out of 200, that's 0.2, 0.1. Moved ahead there. Okay, so let me just make absolutely sure that I would get this right. The idea that what we're dealing with is 40 divided by 200 times 20 divided by 200 would give us no more than 4 people, a tenth of a fifth of the people in the whole category. All right, so that is what we're after. The expected frequency of people who like apples and purple at the same time out of this entire study is 4. Then we can do that for each one of the different categories as long as we know the marginal totals and the total number of people that are in the study. That's what we're doing back with our example, all right? So what we've done is we've taken the observed frequencies here in red, we've used them to make the blue marginal totals. But now the next thing we need to do is wipe for the moment, we'll bring him back, but wipe for the moment the observed raw data from consideration and deal just with the marginal totals and rebuild our raw data set based on the marginal totals and an expectation of no relationship. So we're going to do the same thing here that we did with the apples and color thing and say 32/98 is how probable it is that you're in the hockey row, and 33/98 is how probable it is that you're in the USA column. Well, the probability of being in this row times the probability of being in this column is the actual number of people that you're going to get in the USA hockey box if you multiply that probability by 98. Okay, that is because these two numbers here, 32 and 33, are about USA hockey fans, but one ignores where you're from and the other one ignores what sport you like. Putting them together will give you both. Okay, so 32 out of 98 will take care of sport preference, 33 out of 98 will take care of country of origin, and you end up with a number that gives you the expected frequency for USA hockey fans. Now, down here is how the math actually works. 32/98 times 33/98 is the proportion of total people who would fall into that category. But we're not after the proportion, we're after the actual number of people. So we multiply that by the number of people in the study, which is 98. So you see that? The proportion of hockey fans times the proportion of USA participants times the total number of people will give us the expected number of people in that box. That's 10.78. But notice something here. If you have a proportion that has the total number of people in the denominator times another proportion that has the total number of people in the denominator, but you're always going to be multiplying that by the total number of people, then you can count on the fact that every single time you do this equation, the total number of people will drop out once. Okay, so this is 33/98 times 33/98 times 98. Well, one of those 98 pairs is going to drop out because it's 1. So you end up with this expression, 32, the marginal total, times 33, the other marginal total, divided by 98, the grand total number of people. That will always give you the correct expected frequency for that cell. All right, so in this case, 32 times 33 is 1056, divided by 98 is 10.78. That's the number that goes in that box for the expected number of USA hockey fans. All right, here's the thing about chi-square. It is repetitive. You have to do that for every single cell in your study. When I talk about cells, I mean these boxes, these categories, these overlapping of the different levels of each category that you can have. In this chi-square, by the way, there are 9 cells. 6 marginal totals, 1 grand total, but 9 cells. All right. So if you do that expected frequency calculation for each one of those cells, you've basically got a whole new data set that is made up of not the observed frequencies, but the expected frequencies. So we've got a whole nother data table. Our first data table had the raw data. The second data table has the expected frequencies, and we are driving towards a third. The third data table setup is going to be about how we properly compare how different the raw data is from the expected frequency data. Okay, so again, for every single one of those 9 cells, we have to have some systematic way to tell how different the expected frequency was from the observed frequency in that cell for that category. Here is the calculation for that. Here's the equation for that. In order to get a standardized, useful number for how different an observed frequency is from an expected frequency, you do it this way. You take the difference between the observed and the expected frequency, square it so you can get rid of all the negatives, and then divide it by the expected frequency. This will help to take care of how big the sample size was. This will help to take care of how many categories you had. This will cut everything back down to size and make it a standard expression that we can then use to compare to a critical value table. All right. So every one of your 9 cells is now going to have this number as well, which is going to be its contribution to the chi-squared statistic. All right. So here's kind of starting from scratch where we are going. Here was the data that was raw. We observed these frequencies in our data. We used them to get these marginal totals. We use those marginal totals to backfill in these expected frequencies in purple into a whole kind of alternative universe of our raw data. Now we compare this new universe to the actual universe, and we see for each cell how different they were. For the USA hockey cell, it's 8 minus 10.78 squared, and then divided by 10.78. That's 1. Then we do it for cell 2. Then we do it for cell 3, and it ends up looking like this, right? For each one of those cells, we've taken the number that we observed minus the number we expected, squared it, divided by the number we expected, and got a number. There are now 9 of those numbers. Those are the 9 contributors to the chi-square statistic. And when I say contributors, they are very simple, very straightforward contributors. In order to actually get the chi-square statistic that we're going to look up and compare to a value in the critical value table, we do nothing more complicated than add those numbers up. So when you add 0.72 to 1.45 to 3.43 to 4.11 to 0.23 to 2.14 to 0.17 to 2.80 and to 1.33, you get 16.83. That's it. That's your chi-square statistic. All of the division has already been done. You don't have to take the square root. That's it. You're done. That's your chi-square. It is already standardized for the sample size and for everything else. Okay, so this number, this 16.38, is an expression of how different your raw data was from your expected frequencies. The bigger the difference between your arrangement of data and what the arrangement would be if there was no relationship between your variables, the bigger that difference is, the bigger this number is going to be. Okay, so for our chi-square statistic, it looks like this. Chi-square, that's the symbol for chi-square. It's kind of a wonky looking X. That's chi, the Greek letter chi, is equal to the sum for every one of your cells, the observed frequency minus the expected frequency squared divided by the expected frequency. When you add them all up, you get your chi-square statistic. But at this point, we still don't know whether 16.38 is a big number or a small number. We have to look it up in a table to see whether that is a statistically significant size for that statistic. And here we go. We've got another table. The critical values for the chi-square statistic at 0.1, 0.5, and 0.01 level of significance is all dependent on the degrees of freedom in that chi-square arrangement. So there's a degrees of freedom column here. And so you're going to have to know one last thing, which is how to figure out degrees of freedom for a chi-square. It's not that hard, but it's a little bit more complicated than what we did for ANOVA and for t-tests. The degrees of freedom for a chi-square is the number of rows minus 1 times the number of columns minus 1. So in our situation, we had 3 categories on top, 3 categories down the side. That is 3 minus 1 being 2, 3 minus 1 here being 2. Our degrees of freedom are 2 times 2, or 4. Chi-squares tend to have fairly small degrees of freedom. You're not dealing with a whole bunch of different categories. If you've got 30 categories of something, well, now you run into a lot of degrees of freedom. You're probably never going to find an effect. So chi-square are usually for relatively small numbers of possibilities. So it's not unusual for a chi-square to have 2 or 1 or 3 degrees of freedom. All right. In that case, anyway, if you go down 4 degrees of freedom, which is what is reflected in our example, go over to the 0.05 level of significance, that critical value there is 9.488. Since our statistic was bigger than that, we have significance. This was a significant chi-square. we established dependence between the two variables, and the p-value for our study was less than 0.05. The probability that we got our data, even though there was no relationship between where you are in the world and what your favorite sport is less than 5%. So that's what we call statistical significance. Okay? That's how to do chi-square. I'm going to leave you with a really short comedy break. Take your mind off it for just a second, and then we'll come back and run another simple example through from beginning to end just to help you establish all this one more time.
Yeah.
Plus, I like to go to the zoo.
What is it about the zoo that you like?
Oh, boy. Probably, well, it's a tough one. I'd have to say the animals. How about you?
I did say the animals.
Oh, give me 5.
Okay. Can we get on your way out?
Doctor, I seem caring, don't I?
You do. You seem like a very caring person.
I am, you know. The other day I saw this man going through our garbage looking for food. And, you know, Doctor, I hate to see another human being going through someone's garbage can looking for food. So I made him a really nice raccoon costume. Does he wear it? No. You know, you can't help these people.
Oh, emo.
I'm the one in the middle, you drunken... Oh, my brother says hello. So, hooray for speech therapy.
I think your metabolism has a lot to do with that.
Yeah. I weigh about 140 pounds, naked. I mean, if that scale at the train station is anything to go by. My girlfriend said, Emo, I'm seeing another man. I said, well, try rubbing your eyes or something. She said, no, this other guy, and he loves me, and he wants to marry me. I said, well, sounds like he doesn't even know you. And, doctor.
All right, so here's our alternative example. You're starting over from scratch. I'm not sure how many of you are gamers. I'm sure a lot of you are gamers more now than you were perhaps a month ago. I have never actually played a Fallout franchise title, but apparently I would love it. Fallout New Vegas was a classic. I believe it. I just have never gotten around to it. But anyway, the story was about a year or so ago that Fallout was trying to get on this train that EA started, where you don't just sell somebody a game, you sell them the game and then you collect a little bit of money from them all the time in order to let them enjoy the game. This is called pay to win, PTW, and it really makes most gamers mad. And the older you are, the madder it makes you, because you're used to paying once for a game and playing it for years. But I wanted to know whether the category of people's responses to the pay-to-win scheme broke down according to whether you were a male or female gamer and didn't have any non-binary or didn't have enough people to fill a category that didn't fall into male or female. So I'm just going to make those the categories. So you can either fall into the male category, which included 400 people. You could fall into the female category, which included 600 people, or and that's it. There are 3 categories of responses to the game. You could either buy the game and play it and whine about the play to win subscribers. You could buy the game, pay your money, and be one of those pay to win subscribers, or you could just chuck the whole thing, say screw you to the developers, buy Skyrim and play it again. All right. So here are the number of people for each sex that fell into those categories. 200 males just bought the game and complained, 150 bought and paid, and 50 just bailed out and bought another game. 250 females bought and played, 300 bought and paid, and 50 chucked it and went for another game. All right, so there's our row totals, there's our column totals, and there were 1,000 total people who were in the game. Now, here's the question. Does being male or female affect the probability that you will be in one or another of these categories? So the first thing that we actually need to do is to figure out what the expected frequencies are for each one of these categories. All right, so what we need is expected frequencies. In order to get one for each one of these categories, we need to multiply the row total by the column total and divide by the grand total. This is 400 times 450 equals 180,000. Well, divided by 1,000, that's just 180. So we've got 180 right here in the expected frequency box. For this one, 450 times 400 divided by 1,000. Oh my gosh, would you look at that? It's the same number. Well, since we had the same number of payers and players, then any number that's up here associated with those numbers is going to be the same. So it's not a surprise that we got 180 for both of these boxes. And then 400 times 100 divided by 1,000, well, that's just 40. We expected 40 people there. All right. Now for the bottom, 250 is what we had observed here for this category, but that is 450 times 600 divided by 1,000. That gives us 270. 450 times 600 divided by 1,000, again, 270. Not a surprise. And 100 times 600 divided by 1,000 is 60. All right, that is our expected frequency table. These are our observed frequencies. And now what we need are the numbers that will contribute to the chi-square. So for the top left, that is going to be the difference between 180 and 200 squared, which is now 400, divided by the expected frequency, which is 180. So for this one, 2.22 repeating. For the next one over here, 150 minus 180, that's 30. 30 squared is 900. 900 divided by 180 again is 5. Double checking that. All right, for right here, 40 minus 50, that's 10. 10 times 10 is 100. 100 divided by 40, the expected frequency, 2.5. All right, so now we have half of the contributors to the chi-square statistic happening right here. 270 minus 250, that's 20. 20 times 20 is 400. 400 divided by 270 equals a messy 1.481 repeating. $270 minus 300, that's 30. 30 times 30 is 900. 900 divided by 270 here, 3 1/3, 3.33 repeating. And finally, 50 minus 60, that's 10. 10 squared is 100. 100 divided by 60 gives us 1 2/3, 1.6 repeating. All right. A little bit messy, but if we add all these up, we will have the value for the chi-square statistic. That's 2.22 plus 5 plus 2.5 plus 1.481481 plus 3.3 plus 1.6 equals 16.20. That is the value for the chi-square statistic. Now the question is, how many degrees of freedom are there? Because that's what we're going to need to look up on the table. Okay, well, we had three columns and 2 rows. 3 minus 1 is 2. 2 minus 1 is 1. 2 times 1 That's just 2 degrees of freedom. What are the small ones? That's absolutely fine. No problem with that. Okay, so looking back at the chart, 2 degrees of freedom at the 0.05 level is 5.991. The chi-square critical value is 5.991. Crit. 5.991. And our chi-square value is bigger than 5.991. So with this data set, we can conclude that there is a relationship, there is a difference between your sex and how you would choose to respond to a ripoff game. All right. Hopefully that's relatively straightforward. It's all kind of new. It doesn't have to do with means, and so it's a little bit of a weird area. But at the end of the day, the procedure is really relatively simple. And of course, on the test, I will not make it nearly as repetitive. I'll make sure that you know how to do it by having you demonstrate once or twice that you know what's going on, and then move on with the rest of the test. Okay, so that's about it. This will give you everything that you need to effectively and efficiently get your in-class assignment done. The SPSS assignment with chi-square is also pretty quick. Shouldn't take more than a couple of minutes once you get settled in. And then we will look forward to next week getting everything that we need about correlation and regression under our hats. And after that, it's just the final, which ought to be a real piece of cake. So good luck, everyone. Enjoy your Thursday. I will be sending you times that you can also meet with me virtually in order to answer any questions you have about chi-square and the in-class assignment. Take care.